outside. Okay, you're recording now.
Yeah.
So everything I said about my own university is not recorded. That's very good. Because of course I will forget something and then my management could complain. So I started my PhD studies, I will not say how long ago, but quite long time ago in my hometown in Sweden, which is Göteborg. It's on the west coast of Sweden. It's actually the other technical university, the second one, called Chalmers, in a group which was mainly in superstrings and supersymmetry. So my formal head during my PhD studies was a Professor Lars Brink, who was probably some of you will know by name, who passed away a year ago. But I almost immediately decided that this is too abstract and too complicated for me. So I went into the field which was then very, very fashionable, which used to be called chaos. Now maybe we say more nonlinear dynamics, and which I now consider a sub-branch, at least as a part of physics, it's the sub-branch of statistical physics. And I've continued most of my career in statistical physics and in applications. So I worked a lot towards biological physics and the interface to computational biology. I developed a method to infer contacts in protein structures from tables of sequences of homologous proteins. Now it's been overtaken in this application area, this program that we developed by the pure AI methods developed by Google and others, but it had quite a considerable success for a while, and it's still used. Then I also been quite active in the branch of statistical physics that is devoted to non-equilibrium physics on the mesoscale. Usually we call it stochastic thermodynamics. I've organized conferences. I have a couple of papers which I would be happy to talk about with anybody interested, but they're now like 10 years old. But it's a kind of noted papers in that direction. And then by chance, I sort of drifted from stochastic thermodynamics, which is already mesoscale, to the corresponding thermodynamics on the quantum domain, which would be in the microscale, and sometimes it's called quantum thermodynamics. It's at least this is the term used in the narrow community working on these things. So how to define heat and work and entropy production, which are the main quantities in stochastic thermodynamics for quantum systems. And from that one, I got into more specific problems on quantum. And at some point, my collaborator, or actually he was then not my collaborator, but I was invited by this guy, Paweł Horodecki, who is part of the family of Horodecki people in quantum information. He's the elder son. You know, there is Ryszard Horodecki, the father. There's Paweł Horodecki, Michał Horodecki, and Karol Horodecki, and they're all four professors in quantum information in the same city, in Gdańsk, Poland. Ryszard is now retired, but the other ones are all. And so Paweł, when I came to visit him in Gdańsk, this was during the pandemic, he said, I thought, you know, we were going to discuss thermodynamics. And he said, well, Erik, do you know about black hole entropy and the Hawking information paradox? I said, well, okay, I know something. He said, Erik, it's an important problem. We must solve it. And of course, with this kind of attitude that you must try the most difficult problems, sometimes you succeed. They have been very good at succeeding otherwise. And I will now tell you today about our latest attempt to solve this problem. So we published one paper last year in a good journal, JCAP, is Journal of Cosmology and Astroparticle Physics, with Paweł and his postdoc. And here is, the new result, which is on archive since yesterday, is together with Paweł, Lukasz Hakl, and Mario Kieberg, who are both in Melbourne, and Robert Johnson, who is a postdoc in Stockholm. So I'm going to talk mainly about this paper, and it's about random pure Gaussian states and Hawking radiation. So it's a way of understanding a solution proposed a long time ago to Hawking information paradox using the technology of Gaussian states, which is a part of mathematical physics or quantum information theory. And there are some results already now, like 15 years ago, which we found very useful. Now, they are mainly basis of the first paper, and I will talk a little bit about them, which are not our results. And then I will give an outline of the results that recent we have. So this one is based on bounds that hold for any pure Gaussian states. And this one is for averages. This is for typical behavior of random pure Gaussian states. And I will try to relate both of them to Hawking radiation. So I will give first a sort of introduction to the problem, and then I will tell you about the contents. I give an outline of the contents of these two papers, one after the other. And of course, if you have any questions, I'm happy if you interrupt me at any time. I mean, it's a rather small group. So if anything is unclear, if you think I'm skipping something, of course, I am skipping something to get to the end, but then please feel free to interrupt me. And now let's see, the paging doesn't work. Yeah, now it works. So here's just one slide to which, if you give this talk also to people who are not in cosmology and astroparticle physics, just to convince them that black holes are not only theoretical constructs that you learned about long ago in your undergraduate or early graduate studies, but they are definitely there in the universe, and they have been observed both, of course, in collisions in LIGO, and also rendering of the gas clouds falling into black holes in the middle of galaxies. So these are surely objects that exist in our universe. And so physics is also about these objects in their entirety, not only at solutions to Einstein equations. And here's one slide summarizing all I really want to say about Hawking radiation as such. So this is now a field which is 50 years old almost. And there's two papers by Hawking in 74 and 75. And here's an illustration by Penrose of these things. I'm sure that in this audience, you have all heard this before. You have an infalling matter that collapses. And if it collapses, that forms a black hole, there comes out the horizon, originally a very small point, and then eventually it reaches out and it covers all the black hole. And here time goes on. And in the middle of the black hole, there is something, perhaps a singularity. This is the wavy line. And in a long time scale, the black hole will radiate particles, and eventually in this picture, the black hole will disappear. Of course, there are zillions of variants of this picture that the radiation will stop. There will be a remnant and whatever, but let's say this is the only kind of picture which I'm going to consider in this one. This is what you would get from classical gravity coupled with, on top of that, quantum fields propagating in curved spacetime. As Hawking found, they will then emit, black holes will emit radiation, which is thermal, mode by mode, with a temperature which is given in terms of the black hole mass and the Planck mass. So you can see everything here, Planck mass and velocity of light squared. So this is energy divided by kb, that then gives temperature, and this is massless. This is dimensionless, and it's inversely proportional to the mass. And the only thing you need to remember here is 8 pi, 1 over 8 pi. So this is the formula, the simpler formula for a Schwarzschild black hole, a black hole which is not rotating and is uncharged. And this leads to a mass loss. That's what these arrows mean. That's why these arrows seem to be more and more dense. When you go forward, the mass loss is proportional to mass of the black hole over the Planck mass inverse squared. So of course, here's dm dt. Here you have Planck mass, Planck time. And so that gives the right dimension. This is dimensionless, and it's inversely proportional to mass squared. So initially, the mass loss is very, very small, and towards the end, it's much, much faster, and that's why Hawking, and the title of Hawking's first paper is Black Hole Explosions, because it's an accelerating process which goes faster towards the end. Then I have a slide on Planck units, but I think this is very well known to all of you in this audience, so in the interest of time, I will skip this. I'm sure you know. And so here is the black hole information paradox. I have For my purposes, I have formulated the paradox here. It's not exactly, the way it's written in the literature, but it's something which I find, conceptually a nice way to think about it. So we take a large piece of matter in the pure quantum state, at least we can consider this to be the case, and we assume that gravity acts on this piece of matter. Then eventually it goes into a black hole. And then the black hole evaporates through Hawking radiation. And at the end, the black hole is gone, and all that remains is thermal radiation, counting mode by mode. And that means a pure state, pure quantum state, has developed into a mixed state. And this breaks unitarity and breaks quantum mechanics. So if black holes are objects in our universe, which we should understand fully, this is a problem, because that means that quantum mechanics would not hold in this chain. And the debate on Hawking's information paradox has been going on for these 50 years. The number of papers, when you come from the outside, which of course is my case, is enormous. And after a while, you start to realize, what are the different types of papers, but to read all the papers is impossible, I think, even for the specialists. But it's well known that Hawking, for most of his life, believed that actually black holes do break unitarity, and that this is then an indication that quantum mechanics doesn't hold the universe completely. Then he changed his mind towards the end of his life. He made a bet, which he conceded, and so Hawking, towards the end of his life, actually believed that there was a way out of this, so that there was no breakage of unitarity. There are many people in this business who still to this day maintain that maybe quantum mechanics is broken. Wald is one of those, for instance, and probably many more. Generally, the people who are more specialists than me or have been in this business longer than me in Stockholm, they tell me that people who have come basically from the general relativity side of things, who study this from general relativity side, they tend to take it as quite possible and normal that quantum mechanics is broken. And the people who come from quantum field theory or quantum information theory, when they come in this business, they generally think it's impossible that quantum mechanics should be broken. Instead, there must be some difference and there must be some hole in the argument. And Hawking could then be an example of somebody who started in the first group and moved to the second group. So there are many reviews that state the possible way out of the information loss, and I will here follow one review, which is already quite old, from 1988. Well, it's not published as a review paper, but it is basically a review and a summary. And so the first way is then the fundamental information loss. So we assume that this is actually not the problem, because in the black hole, somehow the universe doesn't follow the law of quantum mechanics. That is one possibility. Yes?
Maybe it would be appropriate to ask at this point.
Of course, at any point. Unless you go like Gian Valley when I gave the talk in Munich, because he interrupted me all the time.
We know that unitarity in quantum mechanics is broken anyway by the measurement process, right? This is an issue which has not yet been completely resolved, as far as I understand. But why should we bother about the unitarity breakout here when it's happening on any scale at any time in any experiment?
The easiest answer to this question is that it's far out enough to give a talk about black holes. If I also give a talk about the measurement problem in quantum mechanics at the same time, maybe it's too much. But still, the standard quantum mechanics, indeed, there is measurement, but measurement is something that you do from the outside to get some information that you can communicate to others. If you don't know, this is a quote from one of the papers of Bohr towards the end of his life. So, but in between, quantum mechanics is supposed to evolve unitarily and in a closed system. Of course, you can, if you have an open system where you don't know the entire environment, then you would have a non-unitary development of the system that you follow by, say, Lindblad equation, if you like, or if you have a Markovian quantum evolution, and this can be considered so that it's actually the environment that watches and observes continuously the system. But I think the problem can be posed in this way anyway. It's not, you can of course say it's not an important problem because it's not practical, but there's so many things in this which is not practical. To begin with, that the Hawking radiation has never been observed and will likely never be observed, at least in this form, because the temperature is ridiculously low and the number of photons that you get out from a black hole this way is also ridiculously small for an astrophysical black hole. Yeah, so it could well be that there is some review somewhere which made a careful study saying that the Hawking radiation is always overwritten by other effects, more like open quantum systems like effects. But I'm not actually aware of that this has been done quantitatively. It could surely be done. So, but this is to point us that there is this explanation. There is one explanation to say that the picture which I gave in the previous slide, the illustration from Penrose is not correct, that there is something that happens at the horizon, which is different than you would only get from quantum particles or quantum fields propagating in the classical space-time around the black hole. There is information return in Hawking radiation, so entanglement between modes of the Hawking radiation, and that this is the explanation why an initially pure state can in the end remain pure, although every mode is thermal. And then remnants, which is to say that evaporation doesn't stop, and that's something like the horizon, that there's something new happens. Some new physics. These two are new physics of standard kinds. This is new physics of a very fundamental kind. And this is the conservative option saying there's really no new physics. It's just a incomplete understanding of what actually it means for a large state to be pure and how many ways a very high dimensional state can be pure. This was first proposed by Don Page in 1980. So this is now a hypothesis which is 43 years old. And since I've highlighted this in green, this is what the talk is about. It's in this tradition. And in the latest 10 years or so, this one has also been the dominant point of view in the community looking at black holes. Yes, one can check from the literature. And sometimes they refer to this as the fundamental dogma of quantum black hole physics, that actually it is quantum. And then this must be the explanation of the hypothesis must be of the type that there's entanglement of the modes of the Hawking radiation which preserve purity. And so that leads me to the first paper, which I'm going to present to you, which now a year ago, which is a very simple application of a less simple paper, which is this one published in 2008 by Jens Eisert and collaborators. And maybe I should ask in the audience, any of you know this paper and this method? If you do, then it will be familiar. If you don't, then I will not give all the details, but I will give sort of the rough idea where this comes from. Okay, so first let me explain that what I mean by marginals here. This would be in physics, it's the reduced density matrix, in this case of single modes. But let me start to say it in classical terms. The marginals problem in classical one is you have a probability distribution by the joint probability distribution of two variables, and the marginals is defined, the variables are x and y, and the marginal with respect to x is the sum of the possible values of y of the joint probability. So this is now the marginal probability over only x. Okay, and the problem of having a pure classical state of two variables, the marginal problem of that one is very simple, because a pure state of classical variables is a delta function. And so here you would have a delta function and a delta function. This one is a product of two delta functions. That's all. So the marginals of a pure classical state are pure, and the marginal problem in this way is not an interesting problem in classical physics. It's an interesting problem in statistical physics if you have a say Gibbs-Boltzmann distribution here on the right hand side, and you want to compute the marginals of the Gibbs-Boltzmann distribution. This is the the belief propagation paradigm, and which has many applications in modern statistical mechanics. But that's another kind of marginal problem. But then in the quantum domain, you have a pure bipartite state. You write it like this in the Schmidt decomposition, and you define from this two density matrices, two reduced density matrices, rho A, which is the partial trace over B of the combined density matrix, and rho B, which is the partial trace of A. And as you know, these density matrices, they are called density matrices because they are typically not pure, even if the total state is pure.
Excuse me, please. What is the function EXI? What is the definition of this function?
This is the joint probability distribution of two random variables, x and y, taking values x and y in some domain. And I write it a bit, by habit, since I also worked on the stochastic statistical physics side, as if they were discrete, which is a usual thing. So you can think of them as Ising spins, okay? And then the probability distribution of x, that's summing of the possible values of the other random variable y. Yeah. Mm-hmm. And so there is actually a general theory on the existence or the absence of existence. So you can pose the question now, suppose I know a marginal or maybe some set of marginals. Maybe I say a very large set of marginals, which are, well, you can start by saying, okay, I have a large set of marginals which are non-overlapping. So here I have the set A and the set B are non-overlapping. And let's say that these is actually a state over very, very many spins. Then I can say, okay, I have the marginals over this, I have all marginals over that. And in the classical case, it gets non-trivial and interesting if the marginals are overlapping. In the quantum case, to my knowledge, this is still an unsolved and difficult problem. Surely interesting, but I don't know anything about it. But then already, if they are non-overlapping, it is a difficult problem to find out if you can find a set of given marginals, non-overlapping. So you divide up all the Hilbert space in different subspaces, and you consider the density matrix in each subspace, and you say, okay, here is my set of density matrices. Is there or is there not a pure state in the whole complete space which has all these marginals? And there is in principle, exact solution by a scientist who I think works in Turkey. He has a Ukrainian name, maybe you know him, Klyachko. But anyway, this is unfortunately quite complicated and almost impossible to use. It is, he treats the general case, and it's a solution by induction. So there is a construction, one layer after another, which is very, very difficult. But maybe, at some point, we will use this complete solution to the problem of Klyachko, which was now 20 years ago. It was never published in a journal for some reason. It's only in a very long paper on arXiv. When physics get difficult, try harmonic oscillators, which I think we all heard this saying in one way or another. So what happened now? That's certainly not me, I hope. Okay, so now we make the additional assumption that actually the total state is Gaussian, which is, of course, geared towards harmonic oscillators, and then it gets simpler. So a Gaussian oscillator states are completely specified by a correlation matrix, which you can find here as a correlation matrix. Here are the phase space volume Z. Z goes from 1 to 2n, and it goes for the quadrature operators Q1, P1, Q2, P2, and so on. So in quantum domain, they have to satisfy a kind of uncertainty relation called the Robertson-Schrödinger uncertainty relation. Only correlation matrices which satisfies this inequality. This means positive semi-definite are allowed. And you can, a real symmetric, and this is of course a real symmetric matrix can be put in the diagonal form by a symplectic transformation. And that is then the C is a symplectic operator and diagonal, where the symplectic eigenvalues come twice replicated. These are the normal frequencies, the frequencies of the normal form of this one. So D1, D1, D2, D2, Dn, Dn. And so you put S transpose here. And the Gaussian pure states, which are the limits of these, which satisfy this just as an equality, they have D1, D2 to Dn equals 1. This, I'm not sure if this is familiar to all of you, but it's certainly is very well established science. And it was not as familiar to me when I started this business, but now, of course, feels like home turf to us. But I put this, yeah.
By Gaussian, you mean that high correlators are expressed through
Yeah,
variables?
yeah.
Simple.
That is the sentence here. Gaussian oscillator states are completely specified by a correlation matrix C.
Okay.
Yeah. Okay. And the density matrix marginalized over one mode is also Gaussian. So, and you can give, of course, it's given by only one submatrix of the correlation matrix, and this submatrix of the correlation matrix can also be diagonalized and also has normal forms. And so for this kth correlation matrix, there will be a symplectic eigenvalue Ck, which is not the same as the dk standing here. So that's how you can have here this being a mixed state with positive Ck, but this can be a pure state with unit dk. So that in this formalism, the quantum modular problem is the following. Suppose I have a matrix here with all these d's equal to 1. And suppose I have a set of correlation matrices, one for each k, with a value Ck for each, greater or equal to 1. Given this set of k symplectic eigenvalues of these correlation matrices, these numbers, can I find a global state? That means, can I find a transformation, a high-dimensional symplectic transformation, that I find that this matrix is a submatrix of this large matrix here, where all here D1s are 1. This is a mathematical problem, which was solved 15 years ago. And it's given, the solution is the following. So you have here, this is the symplectic spectrum of C, is this D1, D2, D2, Dn. And we can, without loss of generality, we can order them 1 less equal to D1, D2 to Dn. And in the pure case, all these Ds are 1. And then we have the set of symplectic spectra of the 2x2 sub correlation matrices, the 2x2 here, that would be the C1, C2, Cn, also ordered 1 less than to C1, less to Cn, less to C2, less to Cn, where all of these can be larger than 1, but they don't have to be. And then there is a necessary conditions and a construction using two-mode operations. So the partial sum, starting from the lowest up to any k of the Cj's must be larger than the Dj's. And for the pure case, this just means that all the Cj's have to be larger or equal to 1. So this doesn't give anything new. But then there's a last one which says that the Cn minus Dn is less than the sum of all the other Cm's minus all the sum of the other Dm's. So for the pure case, this says the largest of the C's minus 1 is less than equal to the sum of the Cm's minus a sum of n minus 1 once. Okay, so you can also rearrange it. So you can say it's the this one, the sum of these ones minus the largest one is larger than something. So you mean you can play with this equation in different ways. It simplifies a little bit if you define the Cm as Bm plus 1, then you get rid of the ones, and so you have an even simpler relation. Okay, and there's also an explicit construction, although they don't spell it out really in the paper, but you have an explicit construction by two-mode, a chain of two-mode transformations. Okay, so then we can check if we have the Hawking radiation, we can check on the thermal eigenvalues here, Cn, and we can say, do they satisfy these conditions? Okay, and that turns to be really doesn't need any calculation, because in this quantity B, which is then C minus 1, it says that the B, which is this in the mode, it's a mode factor. So it's actually the number of quanta in the mode. So the number of quanta in the mode which is most highly populated of the modes of Hawking radiation has to be less than the number of quanta in all the other modes of Hawking radiation. This is what Isot's condition means. And since there are 10 to the 70 more or less modes of Hawking radiation, this is really easy to satisfy. One number is less than the sum of 10 to the 70 other numbers. Yeah. And these are really easy to satisfy to a large black hole. So there is definitely no problem in, and you can show this in this way using Gaussian quantum variables, in having a pure state of all the Hawking radiation where every marginal is exactly as in Hawking radiation. That's the first part. And now you can ask questions, and then I go to the second part.
But Hawking radiation is continuous, right? It's not...
But this is a technical point which comes in here. Of course, it's it starts by being presented as continuous, but then there is a division of the frequencies, which is in discrete steps. So actually, Hawking's prediction are in terms of wave packets. Every mode is a wave packet, so it has a certain width in time and in frequency. Yeah, so those are the waves, those are the modes for which Hawking finds this prediction. These are the number of quanta in certain wave packets, which are centered at some time with some frequency.
Yeah, but there is no limit to the width or to the center.
In Hawking's theory, you are of course the time and the frequency are they're complementary to each other. So if you take a longer time, you can have a sharper frequency. And in Hawking's theory, which is for a stationary black hole, it's a rather arbitrary what you pick as the frequency. Then you have the opposite time of these ones. When you want to, and that comes actually in the next. There's a bit more explanation in the next part. But if you want to model the whole evaporation process of the black hole, you have certain time intervals that you can choose one after another in the lifetime of the black hole, and you have constraints on the length of those time intervals. So you should say in each time interval we would like the modes to be exactly as in Hawking theory, but that supposes that the black hole doesn't change very much in that time. So which means that the time cannot be too long. It can, and we argue for which is convenient for some other reasons for computation, but we argue for choosing the time interval such that it takes the time it takes for the black hole to radiate one Planck mass, which scales as the mass squared of the black hole. And so then the frequency increment that we chose, that we use in the more in the second paper, is 1 over the mass of the black hole, right? So, but in any case, in Hawking's prediction are for these wave packets. So we are just saying that for evaporation process, when you want to have, so the mass of the black hole, of course, changes in the evaporation process. So if you want to use these prediction, and that's of course used here, then you have to assume that you have different time increments as the life of the black hole increases, because then as the black hole gets older, it has evaporated more, so the mass is less. So then the constraints on the time interval that you have to look at the Hawking mode, I mean, the largest possible time interval that you can have for the wave packet in the Hawking mode is gets shorter when you move towards the end of the black hole life. It's a long answer, but I hope it answered your question. Was there something else I missed?
I understand you are discretizing frequency range in some way.
Yes, yes, of course. We are discretizing that, but that's not only our invention. This is, of course, in Hawking also, and everybody.
Although intrinsically it's not discrete.
Well, but the predictions of these number of
Maybe it doesn't
quanta,
matter, maybe it doesn't
I don't think it matters, but the prediction of the quanta is for these wave packets, because if you're not discretizing, eventually you will have, you know, it radiates forever and you have infinite quanta in the mode. But then you have a change of the,
Your omega can be arbitrary. I mean, it's not discrete. The omega that's sitting there, it's not discrete. It's
actually it is. It is. This omega is discrete, and it is in units of the smallest omega that you have, which is inversely proportional to the time of this wave packet in Hawking's theory. You don't want to.
No,
You are very kind compared to some other people when I give this talk. But anyway, let's maybe discuss
no,
this afterwards.
maybe that doesn't matter at all.
I think I don't think it matters when I think I'm right, but of course everybody thinks they're right. Otherwise, they wouldn't give any talks. But I agree that if you agree, and anyway, maybe I show you. So this is the paper which came out yesterday. So now the question which we couldn't address in the previous slide is what happens now between the actual amount of entanglement that you need between the modes. We just said it's possible to have a combined pure state and the reduced density matrices of each mode as in Hawking theory. Fine. But we didn't say in the previous paper how large correlations have to be between modes or how entangled the modes have to be. And this is a problem because you should, from the physical point of view, if you would require a very large amount of entanglement, then you would have to postulate some physical mechanism that actually would generate a large entanglement between the modes. So the next step should be, and this is what I try to show to you the results that we have from this, is can we estimate the size of the mode correlations and the mode entanglement with a slightly more involved method. And so that is the paper which came out yesterday on our archive. And so I will, in two places in these next three slides, I will have this ellipsis when in fact it is the result of a quite long calculation. And I will not do that calculation today. If you want, you can read the paper, but you cannot actually, because it's all in the supplementary material, which we didn't put online yet. So once the supplementary material is checked even one more time, it has been checked many times already, then I can also talk about the points in the ellipsis. And believe me, I wouldn't be able to finish the talk in 1 hour if I would try to fill in this ellipsis, but for the moment you have to take this as a hypothetical truth. I am saying that this is so, and then you can eventually, when you see the paper online, you can check if you believe that this is so. But I can tell you the idea and the results. So the idea is, okay, first, if I have a completely diagonal ones, or as I would have in a pure state, then I can factorize the correlation matrix like this, right? And this S is a real symplectic matrix, which here are conditions that makes it so. Okay, and then I consider a random matrix, any random matrix of the same size, to be symplectic and by the diagonal blocks of the correlation matrix. So I can now construct a measure on these S's that they are constrained to be symplectic. Okay, and of course I then also I constrain them so that the blocks have this form. Okay, and then what do I mean by this? This is the definition of the block. Okay, and then I say that these blocks actually have a form which I determine. These are my constraints. These CIs have to be something, actually have to be what they should be in Hawking theory. Okay, and then if I do this, I can get a distribution of the off-diagonal blocks, and here is the distribution of the reduced correlation matrix of two modes, which I here call 1 and 2. That's the outcome of this. And it depends on all the diagonal blocks, so all that I have constrained on. It has an overall constraint, which says that the resulting correlation matrix, which is this C hat plus this C12, has to be a valid correlation matrix by the Robertson-Schrödinger inequality. So this tells only that this is a possible correlation matrix of a pure state. And it has this form of a product of all the other modes, so everything except 1, 2. And it has one constant term, some term which depends on the diagonal, C11, C12, C11, C22, C12, C21, which of course are the ones that you have in here, and Cj, which is the correlation matrix of all the other modes. I mean, the correlation matrix only of mode J. And so it's a product of all these things. And here's a product of a repeated product of things which are the same constituents as here. And this is the outcome of a rather long calculation. And it's an intermediate result, but which is simpler to discuss. I will very soon move to the even later result. Because an infinite product like this is a little bit hard to work with. And well, okay, there's one slide in between, and then afterwards I will tell you about the Gaussian approximation to this infinite product.
Does this measure is naturally, or you have to count, or you have to postulate it, or you have to...
Well, I think it's never been postulated before, as far as I know.
You just postulate this measure.
We introduced this measure, yes. Yeah.
With this density or
Yeah. I don't think it's been, at least we don't cite anybody else. Maybe we can find somebody who actually did it before, but we don't know anybody.
Yeah, but it's one specific particular measure. Right?
Yes.
Particular measure. You can
Yeah, but then you have to be able to work with them.
yeah.
And this one we can work with. So then we like this one.
All right.
Yeah.
But it's an arbitrary measure.
Arbitrary is a slightly negative connotation word in English. That's what I mean. I would say, be my guest to find something which is more natural and more easy to work with. Then, of course, I will agree with you that it's arbitrary. Otherwise, I would say it's a choice, of course. It's an invention. Maybe it's not an arbitrary invention. I wouldn't go that far. Yeah.
It's just a technical question. What is tau2?
Tau2 is the Pauli Y matrix, a sigma 2. So it's 0 y I minus I.
Many copies, yes.
Sure. Yeah, n copies of them, absolutely. It's the same as appears very early here. This is basically the same as this.
Up to I?
Up to I, yeah. Okay, so when you apply this to the Hawking radiation, you have to recall, I mean, here is actually what we discussed before, is built on wave packets of a certain width delta omega, and to the corresponding time delta t over 1 over delta omega, which must be shorter than black hole time scale, okay? At least that must be shorter than the time scale of the evaporation of the whole black hole, which is scales as M3. And so the mode index I is actually split into N, which denotes the time, and J, which counts the spectral band. Okay, so it actually is a double index. And Hawking's theory, it's for the stationary black hole. And then you can see here, it's like people who like these diagrams will understand them even better than I do. But anyway, this is what it would be in a stationary black hole. You consider the mode here being this one. But so here, somehow maybe going out here, and then eventually appearing here in forward infinity, at the infinity in the future. While in a non-stationary black hole, you can still keep the same band, But the interpretation is a little bit different, because when you go forward in time, then you would have other bands and they will not move anymore in the same geometry because there's an evaporation. And so for a stationary black hole, this choice of delta omega is arbitrary. You make one choice and then that's what you build the theory on. And the delta t is inverse of delta omega. But for an evaporating hole, delta t must be longer, but must be shorter than the remaining lifetime of the black hole, which is m cubed, and it must be longer than the internal dynamic time scale. Sorry, time is repeated here. Now, of course, since there is no theory of quantum gravity, which everybody agrees to, and no theory of the internal structure of black hole, nobody really knows what is the internal time scale of the black hole. But there are several guesses in the literature, and one of them goes as that it should be that this time scale goes as m squared, and another one, which is the more recent one by Maldacena, said that it goes as like m, so linear in the mass with the logarithmic correction. These are the best estimates, from the leading people working on this. Suskins call it scrambling time, and that's a paper rather famous, about 20 years old, and that will give m squared. And we pick this m squared, both that it's the more conservative of the two choices, so m and m squared, and also because it's convenient for many other reasons. Many of the calculations that you do afterwards simplify with this choice. So we make this choice that the time scale is proportional to m squared, which means that more precisely, we chose that the time scale is the time it takes for the black hole to radiate away one Planck mass at the given time. And that means that the discretization in frequency is inversely proportional to mass squared at this particular mass. And these are the different frequencies which are considered. So, and then if you suppose all the C12 small, there's a Gaussian limit of this C12 distribution, then the previous distribution of this infinite product is actually well approximated by a Gaussian, which has this form where these coefficients alpha and beta, these are quadratic forms in C12. These G's here are some kind of response functions. And these coefficients alpha and beta can be expressed in the symplectic eigenvalues, mu1 for one, mu2 for block 2, mu I for all the other ones, as two infinite sums. I mean, this is a calculation which can be done and which we have redone a couple of times. So there's no doubt that this is right. And for the Hawking spectrum, these coefficients are large, except for the first bands. That means the pairs of lowest frequency modes. So the conclusion so far is that the most likely correlations between modes in this model of random Gaussian states is for almost all pairs of modes that you can consider very, very small. So they're practically uncorrelated and they're not entangled. And it's not a problem to explain how they could get entangled or correlated because they are not. And this, of course, leaves out, and that was a big problem for this work for a long time, it leaves out the case of the most highly populated modes, where in fact these frequencies, or more precisely, the smallest eigenvalue of this quadratic form that you get out of this alpha and beta if you diagonalize it. So it's the question, of course, the most compressed mode. So it's the question of the smallest eigenvalue, and this smallest eigenvalue is not large. This means that there is an unconstrained, so it could well be that there are highly correlated modes which are, so high correlation between modes which are highly populated in this discretization. That was the intermediate result which we had more or less before the summer. And it took us quite some time to figure out that this is not a problem. They're still not entangled. And the reason is, and here's another one of these ellipses. So here's the statement which I just made. When alpha and beta are large, the Gaussian limit is self-consistently correct, and all such mode-mode correlations are small. For pairs of highly populated modes, on the other hand, this is not the case. So, but instead we can look for the probability that they are entangled, expressed in basically, because there's a linear transformation here, but basically the two eigenvalues of this matrix C12. So here are these basically these combinations of the two eigenvalues, and you can find by using the Peres-Horoledsky criterion, so the partial transpose P partial transport criterion. You can find out for certain parameter values. This is one illustration which has a big part where it's separable and a small part where it's entangled. But it turns out that when you go to the limit, when all these modes are both highly populated, the entanglement part actually shrinks, and it shrinks to be very small on the background of all other modes as in Hawking radiation. So we are saved from the problem that we had before in summer with this partially new result about entanglement, but at least it's not entirely new, but uses some rather recent result in the end on entangled Gaussian modes. Yeah.
Is it possible to return several slides?
You tell me how far.
To see
How far? How far? How far? How far should I return?
No. To see what the states that picture corresponds.
Here. You tell me where to go. По-русски? Куда идти? Сколько обратно?
Каким состоянием отвечает тот рисунок?
Вот этот рисунок отвечает, конечно, вот мы здесь рассчитали, да? Извините, что мой русский еще украинский недостаточно. Хорошо, весь доклад по-русски я не в состоянии сейчас. Это как бы давно, и на украинском еще меньше. So let me answer in English. So this is an illustration of the Hawking's original calculation. It's the thick line here is supposed to illustrate the wave packet in an eternal black hole. And it's for those wave packets that Hawking computed that they have a thermal spectrum. Okay? Now, the black hole, so this would be, the past, the singularity in the past, this is singularity in the future, and this conformal diagram, and it's I can blame my younger co-authors who love conformal diagrams and draw them all the time. But I believe, just somebody can correct me if I'm wrong, that this is the horizon, and here, this is kind of the backwards particle, and here's the forward particle, and here, this one is the forward infinity, or scry plus, as you say in Penrose terminology, and this is scry minus. I hope this is all correct.
Null infinity.
Null infinity, yeah, okay. Scry okay, so this eternal black hole has this mathematical solution, but a physical black hole doesn't have this singularity in the past, because
It's called white hole.
yeah, I know. Yeah, but because so here this is the conformal diagram of the physical black hole, where this still is the null plus infinity. So this is a scry plus, this is scry minus, and there is a horizon, which is this dotted line. So here you should think of that this somewhere here is kind of the collapsing matter, and here is where the horizon is born. And then the horizon, there is some time out to here's the singularity, and the difference here is that eventually the singularity stops, and there are things going, beyond the singularity, because the black hole has eventually evaporated. And this is actually a very complicated diagram, which should be thought of as being glued together with very thin slices, like this red slice here, each one taken from a different eternal black hole, like this one here. And they're and then they're transposed so that you have this, the form is not quite the same here at the back one. That's, I think, the closest I can make. It's okay?
I just was interested in that place where the coefficients T1, T2, etc. are present.
Yeah, okay. So that's this one. This one.
Where are the coefficients which are
D1, D plus is here, and D1 is here, and those are the symmetric and antisymmetric sums of the two eigenvalues of this correlation matrix between modes C1 and 2. That definition is in the figure caption in the figure indicator.
So the function, this is the matrix C12.
Yes, yes. Well, the C12, of course, has, it's a matrix, so it has two eigenvalues, and those, everything can be expressed in terms of the eigenvalues. Here I gave you the version where you give all the formulas in terms of the matrices, but you can also cook down, there is some invariance in these matrices in rotations, and you can express everything in the eigenvalues. D plus and D minus are the plus and minus combinations of the two eigenvalues of C12, and then you have the symplectic eigenvalues of C1, 1, and C22, which are two numbers. So that's mu1 and mu2. Yeah. And then this is a long story, but there's a disallowed thing, which is here. Of course, that's not allowed. There's some separable part and there's an entangled part, and you have to make reference to some paper 20 years ago, and it's also repeated in textbooks, saying that the Perez-Horodetzky criterion is a one-to-one correspondence to entanglement for pairs of oscillator states, Gaussian oscillator states. It's not true if there are pairs of oscillator states, I believe. So if you have two oscillators on both sides, there's always in this Perez-Horodetzky criterion that they are valid for, let's say, qubit and qubit 3-bit, but they're not valid for a qubit and a qubit. So three-state quantum system, and they happen to be valid for a Gaussian state of one oscillator and one oscillator, but they are not valid for an oscillator states of two oscillators and two oscillators. These are, specialized results from the literature saying that by the use of the Perez-Horodetzky criterion is allowed here, and that's good because this simplifies the determination if they are entangled or not quite enormously. And so I guess I'm at the end. This is 1 hour. So Hawking radiation from an astrophysical black hole can be pure, yet have practically no mode-mode entanglement. And this is under the additional assumption that the state of all radiation is Gaussian, and that we look at random Gaussian pure states. So that's the main conclusion. And there may be other, this new theory, which is a bit new, that we've developed of constrained randomized symplectic transformations, perhaps may be applied in other tasks in physics, like in thermalization of subsystems. And my collaborators like to refer to this paper by Popescu, Short, and Winter. Of course, this is large literature. I like to refer to this problem because I come from the classical statistical physics community. There is this very nice example of ergodic behavior, that is thermalization in a classical non-ergodic system, a chain of harmonic oscillators. You'd believe it's not possible. But it is possible if you look at, in the sense that you look at the non-normal modes. So you make, and then here also you have a measure of possible other modes that you can look at, and with a probability which goes to 1 in the thermodynamic limit, it's indistinguishable from a thermal equilibrium system, mode by mode. It's by an old friend of mine and his collaborators. So it just came out in November. And with this, well, maybe I should say that we were not actually the first ones to use Gaussian state and black hole theory. That this famous paper, I realized much later, by Bekenstein, on which I recommend to you if you like to read some classic, very, very nice paper on black hole, which, like many of Bekenstein's paper, are also very easy to read, very full of physical argument, very little of complicated mathematics and gravitational theory, things which are difficult for a statistical physicist. It's a wonderful paper. So that's a paper based also on Gaussian states. And with this, I thank you. So I thank my collaborators. Also had a long and very fruitful conversation with Don Page many, many times in this work. So I thank him for it also. And of course, funding. Thank you.
Very much for short talk. So maybe some
Now maybe I can take now maybe it's better to take this. Should we stop the recording now? I guess this is the end of the lecture. It's better to stop the recording. Yeah. Okay. Sorry, you have more questions? Maybe you want to say like this.
Okay. So when you say that there is almost